Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, I'm Madan Muswati from the Software Reliability and Research Group, and it's my utmost pleasure today to introduce Shmuel Ur. He's a research scientist at IBM Haifa, and he's been working in the area of concurrency testing for a long time now. And he's the technical lead in the area of coverage in IBM, and is also an IBM master inventor. And he is actually the general chair of the first Haifa verification conference, and he's been the chair of the PAT-TAD workshop for like 6-7 years now. Six, yeah. And he also teaches software testing in the Technion and the Haifa University. Shmuel?
Okay, thanks. So I know there are some people here in the audience who are real experts on what I'm going to talk about, but I couldn't assume that for everybody. So I'll start with things which are more basic. And I'm going to talk about testing and debugging concurrent software. And this is related to work which we have been doing in IBM since '99. And it started with the person who works with me on the project. I mean, we were 2 people, but now we're a bit bigger. When he got annoyed after trying for a full half a year to debug a single bug. And the problem was that they could recreate the bug only once a month. So it made it harder to debug it. So this was one reason for the project that we have. And the other reason for the project that we had was that it was a reaction to the previous project that actually another group had, where they were working on a model-based test generator, where the idea is that I write a model of the software, and then magically all sorts of really good things will happen, including writing tests and finding expected results and so forth and so on. And they actually did this project that they would try model-based test generator in parallel to the traditional technique. So they actually tested the same thing in 2 different ways. And it worked really well. But like almost any other model-based test generation project, it failed. And the reason that it failed was the testers didn't know how to use the tool. So it's a complicated tool to use. So what we were looking for at the time was a tool that is under the hood, in the sense that it's possible that at least 1 or 2 of you don't understand how the engine in your car works, but you can still drive them. So we were looking for a tool in which the tester would not have to know how the tool works or anything about it, and would still be able to find bugs. So this was the context in which this talk is about. So I'm going to explain why concurrency testing is hard. And I assume that most of you will know some of it, but maybe some of it will be new to you. So the obvious thing is that when you test a concurrent program, you have indeterminism. So sometimes it will fail, and sometimes it would succeed on the same input. So the fact that you run a test that you didn't find a bug does not mean that this test will not find a bug in the future. The converse is also true. The fact that you run a test and you didn't find a bug will not mean that somebody else will be able to, that it will happen again. So you have 2 types of problems here, and most of them and both of them are very annoying. So the first one is the following. You take your test and run it as many times as you want, and usually if your system is not complex, you'll get the same result. Somebody else takes your test and runs the same test many, many times, and he will get the same result. However, it's not necessarily the same result as yours. So what does it mean? It means that you have taken this program, and you have been testing it for 2 years, and you think you've done a really good job. And then your customer takes it and runs it on his new configuration, and he finds the bug the first time he tested it. And he says, you're not even trying. So this is annoying. The second reason that causes it to be annoying is the problem of reproducibility. So you run the test, And let's assume that in test you found the bug. And then somebody has to fix it, right? So you move it to his system and the bug goes away. And he can't fix it until he can find it. So let's assume that your car does not start in the morning. Usually, eventually you can get it to start and you go to the mechanic and you tell him fix it, but it starts really nicely because you've driven it all the way there and now it's warm. So in my country, if a mechanic is willing to fix something that they can't see happening, this is not the mechanic you want to go to. You first have to be able to recreate the problem. So those are some of the issue. The next issue is that how good is your testing? How do you know how good is your testing? So let's assume that I take your code, and for the moment take my word for it. I remove all the synchronization statement from your code. Okay? So we have a tool that can do that for Java. You can create a tool that does that for C. So functionally the code is still the same, right? I mean, you just remove all the synchronization. Let's assume that you run the test, and the test gives you the exact same result as if you didn't have as before. So what does that mean? It means that you're not testing the synchronization at all, right? If you can remove all the synchronization and the test result will stay the same, it means that your testing is actually no good for synchronization purposes. And my guess is that this is the case. So I don't know, you have really powerful environments here, but you have to check that what I'm saying is correct. Maybe it's not. But how do you know which synchronization did anything? So synchronization, if nobody is trying to actually get to the same place as an OP, how do you know if your test is getting there? So we talked about that. And the result is that synchronizations in our big projects in IBM represent on average about 10% of the bugs that exist. But a much larger percentage of those that will actually make it to the field, because they are very hard to find in the beginning. So it's not a very large percentage of the bug. I mean, 10 is not small, but it's still a high percentage of the bugs that the customer found, and it's also one which is much harder for people to fix using all sorts of debugging issues. So I'm going to give an example. The fact that it's in Java doesn't make a difference in this case because it will be the same in C. So you have counter ++, and if you execute it, what you expect is for the counter to increase, right? But if it works in a concurrent code, you do two of them at the same time. So a ++ is actually implemented as 3-byte codes, or will be implemented the same way in C. You do a load, and then an increment. But if you have a context switch, you do a load, and then an increment, and write back you get 4. Write back again, you get 4 again. Okay? So what you did is you instrumented it, you executed it twice. Instead of getting 5, you got 4. This is only part of the problem. The real problem is that one of them is ignored, right? So you overwritten a result, and you missed something. So just the fact that something looked like it is going to be executing it once does mean that it's going to be doing that. Okay, so I'll give another example of, I'm going to start by giving an example of bugs. So we have a hello world, and I apologize, this talk was not written specifically for you, so it's in Java. I know that not all of you are extremely familiar with Java, but it will be the same thing. So we have two threads. One of them writes hello, and the other one writes world. And what happens in the main thread is you start the hello thread, and then you do the world thread, and then you go to sleep, print a new line. So if you take this program and execute it, you'll always get hello world. Okay? This is if this is the only thing running in the system at the time. But what are the possibilities? What can be the output of this program? What other output are possible except hello world?
Hello.
Okay, so when I say start here, What do I mean when I say start here? So who execute next? So this could be executing next or not. So if it doesn't execute next and this one execute next, then you get world, and then you get hello. So what would actually happen in your system? I'm asking you without knowing the answer, and I know the answer on some system. When you do a start for a thread, will the execution move to the thread first, or will it continue in the main threads? So what I can tell you is it depends on the policy. So in Windows and Unix, it's not the same, actually. And in Windows, for Java, it's deterministic. And in Unix, it's not. OK, so you can have word hello. OK, what else can you have?
Maybe you can have word and hello delete.
That's nice. That's true. So it's not atomic, actually. So you could have first H, and then W, and then O, and then E. OK, yeah, that's true. What else can you have?
New line.
New line. OK, so what we did here is we wanted the new line to be at the end of the program, right? And in order to ensure that, we did a slip statement. Slip statements don't ensure anything. OK, so slip statement, the only thing that it actually ensures is that while this slip state, so for a second, this thread is not executing. This means that the others are executing. So you could have new line, hello, and then world, or hello, new line, word, or any combination where the new line is one of the characters. But, OK, so now the following.
Just get new line on a really weird system. Right?
OK.
Because you're not waiting for the children thread to finish.
So this was an interesting comment, and it's not true in Java, but it would be true in C. So what Tom was saying is, what happened if I had a new line, and then the main thread finished? What would happen to those threads? And they are called orphaned, because their father is dying. but what happened to them? So in some system, like in P threads, I don't know how it's in yours, those would die as well. But in Java, they don't. They just stay orphan thread. And in this case, they didn't need any data structures that belong to the main thread, which means they're doing fine on their own. So you could have new line and then hello and then world. They wouldn't die. But what we have just seen now is that in order to program correctly in concurrent, you have to actually know the definition of how everything is happening, and most people don't. So you can have all sorts of interesting options here. OK, so this riddle will be maybe too difficult the way it is because it's Java specific, but I'll ask you a few questions. So the first thing that you really have to understand is that synchronization and atomicity are not the same. OK, so when you have a lock, nothing becomes atomic as a result. So for example, if you have X++ and you put it in a lock, that doesn't make it atomic. It just makes sure that not two things can go into the same thing. OK, so now you have a lock. You have taken a lock, and then you have taken an exception. From inside the lock, you go out to some place, to the exception handler. Are you still holding that lock? So the reason it's important, because if you're still holding the lock, you need to release it as part of your exception handling. And if you're not holding the lock, you don't need to release it. So
I think in Java the lock's released when the exception goes outside the synchronized block.
So you're right. In Java, the lock is released. What happens in your system? Do you know?
Yeah, same.
In .NET, it's released, and also in C.
So C actually doesn't have any exception mechanism. So
well, right. So
there's a structured exception handling in Microsoft C. And
is it released or not?
No, it's just a library.
Well, right. So the library will need to decide. So the answer is, as you've seen here, is that in the place that you program, you need to know the answer to this question. If you don't know the answer to this question, you don't know how to do exceptions correctly. And some people believe strongly enough that nobody knows how to do exception correctly, that they say that you should program with exceptions. But I assume you are programming with exceptions, then you should know the answer to this question. So now the following question is so now I have another question, which is, the answer is Java specific, but you can think about it in your own environment. So we have a class called conflict, which has a synchronized constructor called conflict. And inside there is a method which has a synchronized block. And there is also a synchronized method in this class, and also a static synchronized method in this class, and also just a regular method which is not synchronized. And the question is, which of those things can happen at the same time? So for example, we have a synchronized method here, and a static synchronized method here. And when I am in G, can somebody else go into F? Okay, so this is the question. And the actual question is, are they synchronized on the same object? Because if they are synchronized on the same object, then once my thread is in here, it's protected, and no, the thread cannot go into this place. The answer is that they are not synchronized on the same object. So you have two different objects here. One of them is the class object, which this is synchronized on, and this is synchronized on, which means that you can't do those two in parallel. And the other one is the class instance object, which those two are synchronized on, and you cannot go in. If you go into this, you cannot go into this one. Again, my guess is that not everyone in the audience was aware of that, and this is the kind of details that you need to be aware of in order to do those things correctly. So I'm going to skip the next example, except to say that there are two bugs in this program, and when I made it in order to give talks about it, I found only one. But then it was fine, because once I found the second one, it turns into a feature, right? So now I can talk about it in talks. I was pretty happy. I said, I'm a researcher, I create bugs, I find them, there are features, no problem there. So what could happen to a researcher is that you publish something which is wrong. And when somebody else finds the bug in your journal paper, that's less fun. So the claims that I have in this, and I apologize for this really overloaded slide, it's there just to show that it's part of a journal. So my claims there is that many people program with data races intentionally, and it's not always a bug. So I'll give you an example. So let's assume that you have a sign over the road that gives you the temperature. And you also have this things that measures the temperature. And what happens, this thing measures the temperature and it does it 1,000 times a second because that's the device that you bought. And you write it into this buffer, and this copies from the buffer and put it on the screen for the people to see. Now, people in general don't care about the temperature measured being 1,000 times a second. It doesn't make any difference to them. So once every, say, a minute is fine, right? Temperature doesn't change that fast. So if I take it and I put it here, and I copy it to here, and as long as both operations are atomic, there is a race, because I don't know which one of them I'm copying. But I don't care about it, because I don't care if I had the temperature of the 0.997 second or the 1.999, or I just don't care. So I put it here, and I displayed it every 1 minute, and I'm fine. But let's assume that the following problem occurs. What I write here is 19 and 20s, because those are the temperatures. If it's not atomic, maybe I copy this, and then I copy this. And then I could have a temperature like 10. Right, because I copied the first digit here and the second digit from this one. It's not atomic. Now, this is bad. But it doesn't have to be. So if it was atomic, so if you say A equals B, is this an atomic operation in your language? Do you know if it's an atomic operation?
I think it depends on the way.
Yeah, like everything. The answer is maybe. So it depends on what A and B is. So usually for like a short or an int, it will be atomic. But if it's long or a float, then it's not. And then, so if you have A equals B in two threads running in parallel, you could have all sorts of interesting results happening. Okay. So this is why I said the data race does not have to be a bug. And I gave an example where what I do is I copy two variables, and I copy them from one thread to another using a spin loop here. in which I wait to see that I did part of the copy and then I did the end of the copy. And I said, this is fine, this will work, and this is not a bug. And then somebody told me, well, you forgot the memory model of Java. So how many people are aware of the memory model in which you work with? And why should you care at all? Okay, so some people are aware. And the reasons that you should care is actually new. So what happens in Java is that in the theoretical implementation of the language, when you have a global variable, you have a local copy of that variable in each thread. So when you change it, the other thread do not necessarily see the changes. Okay? So if I write in one thread, this global is equal to 3, and in another thread I'm reading it, I don't see that there was a change. I might see that there was a change. I mean, it's completely legal to do an implementation in Java in which a thread does not have a local copy. And this was the way it was done in the past. Now, why would you want to have a local copy for each global variable? Why would you have this feature of the language? And the reason is that most of your laptops now, I think, are dual core, and they'll be having more cores in the future. And if you have a dual core computer, then you'd want to have the local value, and not copying it would actually make your program faster. This is fine, except that if you do a spin loop, and you're checking if some value was changing in another thread, you wouldn't know that it changed. It really did change, but you don't know that because the global variable was not copied. So it's this bug, and I couldn't find it in my machine, but the people who wrote the paper could find it. Another example of bugs, let's assume that you move money from one account to another account. The fact that the two lines are one after the other doesn't mean that they'll be executed one after the other. So you have to be very careful. And it could be that between them you have a thread switch and the amount may be changing, or the places the money goes to will be changing. So this is not atomic. And making it synchronized will not make it atomic either. Okay? So you have to be very careful about it. So let's assume that it was atomic. So let's assume that I had a situation in the bank where I do transfer of funds from account to account. So I take money and I move it from here to here, and I move it from here to here. And the bank has this assumption that the amount of money in the bank will stay the same. Right? So you transfer between accounts and you assume that the total amount will stay the same. So let's assume that the transfer is atomic. And what I do is I have this loop that goes over the entire money in the bank and checks that the amount stays the same. So what I do is I summarize all the account and I check that they stay the same, and during this time I might be transferring money. Will the loop give me the correct result? Why not? You're saying no, but why wouldn't it?
It could have changed when it is doing the sums. So it could have been looking up synchronized. And that it could
There's no
change.
synchronization. I'm saying let's assume that the changing of the money is atomic. So I'm moving money from one place to another, and it's atomic. So this yes?
Just mechanically, that other operation is an atomic. It doesn't have a snapshot of the
Right.
data on which
Yes.
no operations occur.
So why is it a problem?
It looked at fund from first, then money moved from fund to fund from, then it looked at fund to.
So let's assume that you started counting and you got to here, and when you got to here, somebody moved money to here. And then you continue, then you counted this money twice. Okay? So the problem here is that while the situation is correct, your observation of it is wrong, which is a very big problem, by the way. So for example, when you go into a cash machine and you put your card inside, it goes VV, right? So why does it go VV? So one option is that it's counting money, but it's not. Another option is that it's doing a transaction, which it does, memory transaction. I mean, it communicates to another place, but communication is not usually that noisy. So why do you know why you have this noise when you put the machine? It's a self-protection There is this device whose job is to go vroom, because people are very upset when they put their card and they see nothing happening. And this could be very dangerous to the machine, right?
It's the same principle with the hybrid cars.
Yeah.
Right? If they're too silent, people can get run over. So they're talking about putting noisemakers.
So it's just to prevent people from like messing around, pushing more buttons and so on?
No, actually prevent them from punching the machine.
It's also good to have
Yeah.
people not get run over.
That's true. So you want it to be observable, and sometimes when you have a program and it's working, it will have all sorts of signs, right? So this is it. So concurrency, actually, bugs are not necessarily related to programming. They're related to problems which exist in the real world. And I'm going to show you an investigation report of a train accident, which had to do with a concurrency bug. This is from the late 19th century. Not so late, actually, but second half. So the problem is the following. They started having a train in Britain, and it turned out that if train collides in the middle of a tunnel, it's really bad. So the first solution that they had was to have two sets of tracks. So if you go this way, you go on the right, and if you go this way, possibly in England, it's the other way around. But you know which direction you go to, and you don't have any more frontal collisions. The second problem is that when you go into a train and you hit each other in the back, that's also bad. So what they have is this protocol with two people, and they are sending signals, and we'll see how it works. So the trains enter the tunnel, and now there is a semaphore here, and this is why we have a semaphore, and the semaphore physically turns red. So the train runs it over, and it turns red. This is what it's supposed to do. And in England, it sometimes will not work. And when it will not work, it will usually be due to the fact that it was freezing. This is extremely unlikely in Israel, where I come from. But in England, it can happen. So it's supposed to turn red. And then the signalman sends a note to the other signalman saying that there is a train in the tunnel. And then the train exits the tunnel. And you get a signal back, and the signalman physically turns the semaphore to green. This is how this is supposed to work. The second option is turn red. You send a signal. The second train approaches the tunnel, stops at the red light. By the way, there is already a bug here in the protocol. So we have a very short protocol here. Think about it. We'll discuss it later. There is already a bug here. It exits the tunnels. You get... okay. The third... Oh, sorry, I apologize. The bug is here. The train enters the tunnel. What happened was that the semaphore failed to turn red. Right? So you send a note that there is somebody in the tunnel, and he runs outside, turns it to red himself, and then he gets a signal, and everything is fine. Okay, so all of those is just to understand what the protocol is about. And now I'll show you what really happened. So the train enters the tunnel, the semaphore fails to turn red. He sends a note that there is a train in the tunnel. He's running, but as he's running, another train entered the tunnel. So what was the bug here? The bug was that running was the very first priority thing to do, but sending a signal was not. And he first sent the signal, and then he ran. He should have done it the other way around. Okay, so we have a second train in the tunnel. He noticed this guy running, but he didn't succeed in stopping. So he knows something wrong is going on, the driver in the tunnel. So he actually guesses that there might be a train ahead of him. So he's worried. So he's in the tunnel. Now the signalman sends another signal to B. Now we are outside the protocol. Right? B got two signals, and he didn't see anything yet. So something wrong is going on. And we have a third train. Okay, so we're in this not so good situation now. This driver doesn't know what's going on, so he stops in the middle of the tunnel to think about it. The first train enters the tunnel. Now what is B supposed to do? He got 2 signals and he sees 1 train. He sends a signal, right? Now what is A supposed to do? A sent 2 signals and got back 1. What does the signals that he got means? So he assumes that both of them left the tunnel. Okay? So he turns it into green. Now, this guy is still suspicious. He doesn't know what's going on. Just so to be on the safe side, he decided to back up slowly out of the tunnel. And boom. Okay, so there are many concurrency issues that have to do with the real world. The real world problems have concurrency in them. It's not just the program, it's the real protocol. And to find this bug, well, this bug was found by the customers, right? But this could be expensive. Sometimes it's not the way you think. So for example, I was invited to give a talk in Lawrence Livermore National Laboratories, which is actually sometimes hard for Israelis to get into because we are not signed on the Non-Proliferation Treaty. And I give them a talk, and they're not worried at all about bugs. They just care about performance. Okay? So I ask them, what do you do? And they say, we do a simulation of atomic explosions. Okay? And then you think about it, and what's the probability that the customer will complain? Right? So you don't have customer complaints, you worry less about quality. Performance is important. Service, yes. They had other problems which was interesting. So you know, one of the problems that you don't usually need to solve is to detect that a deadlock occurred. If a deadlock occurs, you know, right? It deadlocked on you. But when you run a system with 128,000 processors running concurrently for a single application, it could be there's a deadlock for only a few thousand of them. And the program is still running. So a deadlock is actually a performance issue because it's running slower. So they have to do the deadlock detection as the program is running, which is usually not a problem for others. So I assume that you know that bugs could have different reasons as to why they are important. So really, so there's the consequence. For example, if somebody dies, it's not a good bug to have. But there are other reasons, such as who found it. So if your manager found it, it's semi-bad, and if somebody really important found it, it's really bad, even if the bug is not really important. So this bug was important to us because it was the first bug that we found with our tool on a real application, which is WebSphere. So it was written, if connection is not equal to null, then do this. And the reason is we don't want a null pointer exception. So what's the bug here? Well, it's a fairly obvious one. Okay, so you could have a thread switch here, and then you could take a null pointer exception. Okay, so this is one bug. There's another bug here, which is after you change here, somebody changed connection to a different connection, and then you stop the wrong connection. So it could be a security bug due to concurrency, because this is allowed to do the stop, and others are not allowed to do the stop, but they can change the connection, and therefore they can stop the wrong connection. So we found about 300 of them in the code. Now, this kind of bug can exist in the field for a long time before somebody finds it. Because for this bug to occur, you need a very strict thread scheduling sequence. You need the thread schedule to be exactly here. And then you need something else to happen. So once you know this pattern, you're not going to make it anymore. But if you don't know this pattern, this is an easy bug to make.
How did you fix those 300?
Okay, so that's an interesting question. So let's start with how we fix one. So now we know that we have a bug here. So how do we fix this bug? What's the change in the code that I have to make?
Create a lock.
Okay, so if I create a lock here, so I have a lock here, it's not going to help me any, because that wasn't my problem to begin with. I can have a thread switch inside inside a lock, and then somebody else changed connection to null. So the answer is that locks do not have to do with code, they have to do with data. So any place that I touch connection, I have to do a lock, and then I will lock all of them, and this will be fine. This is the way I actually fix it. But there is a lesson to learn here. So let's assume that you did that, and everything was fine. And 2 years later, a new programmer came into your project, and he didn't know about that. So he writes connection is equal to null in this place, which is very far away from here. And 3 months after he did that, you get a null pointer exceptions here. So who's to blame? It will probably be you. If you're still, yes?
I blame the programming language.
That you don't have atomicity. Right, what you want is atomicity here. Yeah. But that means that the entire project has to maintain the discipline. And that's the only way to do it in the programming language that we have. Okay, so some typical bug patterns. So we talk about atomicity right now. So for example, this is not atomic, even though it might look a bit atomic to you. As we said, equal may not be atomic. Two instructions being right after the other certainly is not atomic. So you have to be careful. Two-stage lock is actually a very common bug. So the problem is that you have two accesses and they need to be atomic. So what you do is you make them each one. So you need to. So what you do is you do lock on all the data the appropriate data structures. But because you don't want your lock to be very big, you don't do it in one lock, and then you can have a window in the middle which changes it. This is a common way for a data structure to get corrupted, that the lock is not fully locked. And data race tools will not find those things for you. Those are called high-level data races. So an example would be if you have if you're working, let's assume, on points, and a point has an x and a y coordinate. So you have one function that does something to x, and another function that does something to y, another function that does something to x and y, and all of them are synchronized, right? But if you don't do them on the same lock, you do something on x and y, and in the middle something can happen to x, or you do something on x and y, and then you do something on x. So you did something. So this was the first thing, and then you did that, and then you do another one like that before you did this one. So you have an inconsistent number. Okay, so we talked about this one. Sleep statements. There is no guarantee that the sleep does anything, as I said. If you find a slip in the code, there should be a very good explanation to why it's there. If it has something to do with customer experience, this is fine. You don't want things to appear too fast on the screen or so forth. But in general, if you did that to make sure that something happened by the time you are done, that's a bug. So in Java, we have a notify and await. The notify is asynchronous. So what happens if the notify happens before the wait? It does nothing. So you have a notify, and then you have a wait, and you can wait for a fairly long time. How long do you think you can wait? If the notify will never happen, how long will you wait?
I mean, it's a deadlock, it's 30 not in progress.
Okay. We'll get back to that question soon. So blocking critical section. In a critical section, you don't want to block. Orphan threads. This is, again, depends on the implementation. I don't know. I know how it is in Java. I'm not sure how it is in .NET. What happens when you have an orphan thread in .NET? Does it die, or doesn't die? So the problem is that if the thread that started it dies, the other thread does not die, but it could be that some of the data structures that it needs did die. So it wants to use something that the thread that made it had. It's not there anymore, and you could have problems. So unintentional difference threads. So sometimes when you have an API, the API will start a new thread. So one thing that can happen, which is really annoying, is if you have the single-threaded program and it gets into a deadlock.
So how does this happen? I don't understand.
So a single-threaded program cannot get into a deadlock in theory, right? At least in Java. In C it could, but in Java it cannot. But what happens if you use a GUI? So if you use a GUI, your API creates a new thread that you were not aware of. And this thread may be competing with your thread on resources, and you could have a deadlock in a program that looks single-threaded. Now, if one of the VP of your company finds it, which was the case for us, I mean, not for my code, but for somebody in my, say, 2 floors above me, this becomes an important bug. And he said, but it can't be a deadlock. It's a single-threaded program. And the reason the VP could find it, which nobody else did, was that he was the first one to have a dual-core machine. So he had different timings. We talked about how you can get out of wait. This is the definition of the language Java. So you can get out of wait in 5 ways. You can do a notify and notify all. The wait may be interrupted. You can have a timeout. Or in Java, there's something called a spurious wake-up, which means that the machine decided that you have waited enough and decided to get out of it. And the guarantee is that this will rarely occur in practice. Okay? So this is part of the Java definition, part that many programmers are not familiar with, which is why I had to put it here in red, because they didn't believe me. And what...
When it does the spurious wake-up, does it throw an interrupted exception, or?
No, it just wakes up.
It just says you're not.
Yeah, you're just done.
The timeout option happens only if the wait was called with a timeout
Right.
parameter, right?
Yes, yes. So timeout is if you decide to have a timeout.
Okay. And what does interrupted mean?
Means that you took an interrupt while you were in the wait. It's like taking an interrupt while you're in a sleep. You just get out of it because of the interrupt.
So you abort the thread, or?
I see.
So this is with respect to a condition variable, right? This wait is for a conditional.
This is, you wait on an object. So what it means that in Java, if a wait is not a while loop, it's a bug. Because you waited for some reason, and once you finished waiting, you have to check that this reason actually occurred. There's no guarantee that you are notified. It's actually true in other languages, there's no guarantee that you're notified because you might have gotten there through an exception, and you want to check while you got out. But because of the spurious wake-up, this is a bug.
Do you have a work thread in Java?
No, but you can throw an interrupt.
Thread.work. Clear that. Slow.
Okay, another example of something that... so now I'm going to start talking a bit about testing. We talked about bugs. So let's assume that you want to test a program, and this program is supposed to be sort of dependable, which means that it's running, it's a distributive program, it's running over the network, and the components are not dependable. So the network may not be reliable, and some of the components may die or not die. But the program is supposed to continue to work gracefully. So what you want it to look in your testing environment is as if the network is not reliable. The problem that you have is the network that you have in your testing infrastructure is a really reliable one. Okay? And your CPUs don't tend to die on you so often. So how would you test the program? This is the issue. So one solution is to have many students doing that with the power, but it's an expensive solution and they don't do it fast enough usually. A second option, which we had, was when you have sockets, you can in the socket intercedes and decide what happened to the messages. And this would look as if, for example, if you block the messages, it would look as if something is not working currently. So one thing that we did here is you have a delay, and then means that the messages are going away, or not going away, are delayed. And when you stop the delays, they will continue. So you have to know which behaviors are legal under your protocol. So for example, in TCP/IP, you know that the messages may be delayed, but they will arrive at the same order in which they were sent. and nothing else will happen to them. In UDP-IP, you could have messages arriving in a different order. You could have the messages arriving multiple times, and you have to make sure that your environment is happy with that, and that doesn't happen all that often in a real environment. Okay, so to finish this part of the talk, so what are the observations that we have? The first one is that thread switches do not happen a lot. So in Java, it's on average every 20,000 instructions, unless something else happens. And many bugs you will not be able to see if you do that. So if you have a concurrent bug, the probability that you will see it is low. And usually the synchronization statements that you have in the code, you have a few instructions here, are no-op. Why are they no-op? Because you went in, and the only reason this will be not a no-op is if somebody else tried to get in. But for that, you need the thread switch, and you need somebody else to take control and try to get in. And this is unlikely because usually this block is very small. So synchronization usually doesn't do anything. Yes?
Is this observation only for single-core processors? Or?
No, well, it's more true for single-core processors, but that's still, the fact that this will be done very, very fast is true anyway. Yes, in multi-core you'll have more things happening. Now, the second observation is that if you are, as a programmer, don't know what you are doing as far as regular programming, then you'll find out. So if you didn't do what a for loop does, the program will not do what you expect it to do. But if you don't understand what synchronization does, that's fine, right? Because you will not find this bug. Probably the customer will, but maybe by then you'll be in a different project. So if you don't know the exact what the synchronization means exactly, then this is not going to impact you immediately. For example, some of you might not have known what happens when you take an exception, if you still contain the lock or not contain the lock. But this is rare enough that in your testing it will not happen. It will happen in somebody else's testing. So this is one observation. The other observation is when you test it, it's almost deterministic in a simple environment. You have the tool here, chess, that people are doing here to find those kind of bugs. But without the tool, you can run your program many, many times, and you will not be able to find the bugs. But the fact that you have not found the bug does not mean that the customer will not find it the first time it executes it. Okay, so now I'm going to talk about how we go about finding the bugs. So we use a technique called the noise making. And what we do is, when the program is running, we instrument it in all sorts of places whose order may impact the result. And every time you get into our instrumentation, we might change the timing. So we might put a sleep statement, or a yield, or something else. And that means that whenever you execute the program, we will try to cause different interesting timings to happen. And then you can run the programs a number of times, and hopefully nasty things will happen. Now, this is a dynamic technique which does not assume that I know what your program is supposed to do. So I don't give you warnings. I told you this is my under the hood idea. You run the test, and I try to make the test fail. But I don't know what your test is supposed to do. So, well, this was the theory before we encountered users. But, user caused problems. But the theory was that you have a test, and you run it, and we try to make it fail. Okay? And if it fails, you know that it failed. I don't know what it's supposed to do, and then we'll help you debug it. But you just run the same test the same way you did before, and everything is fine, right? This was, as I said, this was the theory. The first exception to this theory was we assume that you don't want deadlocks. So if we detect the deadlocks, we're going to tell you that there is a potential deadlock. And also we have an idea of what bugs look like. So we try to cause them to happen, but we don't report them. So we try to cause your program to behave in a different way, but you will tell us if you're happy or not. So if there is a race, for example, one time we'll put it like that, and one time we'll put it like that. And if you're happy both ways, then it's fine with us. This is the tool. And there is no idea of exhaustivity or anything. When you run the test, we try to find more bugs.
So do you just interject this randomly, or
Well, we
if
know
you
what-
find a bug, can I reprovide it?
We'll get to that. This is debugging. So, but I'm talking about testing right now, and we're trying to cause the program to fail, but we don't know what fail means exactly. So we look for bug patterns. So for example, if there is a wait and a notify, we'll try to cause a lost notify to happen. So we'll try to happen. The notify happens before the wait, and then maybe you're happy with that, but maybe it finds the bug. If you have a sleep statement in your program, we're likely to kill it, just because we don't like sleep statements. But we could also change its timing. So the idea is that you run a test. Usually you just look in the dark. With our tool, you run the test a number of times, and you might find that some of the dark has bugs in it. As I said, this was the idea before we hit the customers, and then they wanted features. Right? So the first feature had to do with deadlocks, and I will get into it later, but the first idea you should know about deadlocks is you should maintain lock discipline. So everybody here knows what lock discipline is? Or let's ask if somebody doesn't know what lock discipline is? I get no raised hands either way. So okay. So when you have locks, you might take lock one inside the other. So you take lock A, and then inside it you take lock B. Right? And if you do it the other way, in another thread, maybe you took B, and inside it you took A. And lock discipline says that the order in which locks are taken one inside the other should be the same. So here it's not the same. And if we create a graph, we would have A and B, and it would be a cycle. This is a graph you really don't want to have cycles in. So you should know the order of the locks in which you take things, and it should be this. You should have one order, and you shouldn't take it in any other order. It could be that it's not a bug here, because it could be that for some reason those two threads cannot run at the same time. But it's still really, really not the way to program. This is something we'll report in. We'll report about, also try to cause to happen. We have orange box, which comes from the fact that the black box in an airplane, its color is orange. And the reason is that it's much easier to see orange than it is to see black. So, for example, let's assume that your program crashed with a null pointer exception. What you could do with an orange box is ask, where did I get the value null? So you know that you had a null pointer at this point, but you don't know when it was assigned. So you look for the last few values for a variable, and then you can do the orange box. Replay. So you have a bug, and you want to replay it. Now, for reasons I don't have time to go into, replay is a really, really difficult problem if you want to do it in a reasonable amount of time. But what we do is we don't have replay, but what we do is our noise is using a random, and we start with a seed. So when you run the test again, you can run the test the same way you ran it last time, with the same seed. And if everything else is sort of the same, then you're more likely to see the bug again. So for very simple programs like the hello world, it will be deterministic. And for large programs, we moved from one month to half an hour as a debugging time. But it still was only 1 in 20. Our program works, as I said, it looks like that, right? So every time you have your own code, and then you're running my code, and you have your own code, and then you're running my code. So I know what your code is doing all the time. So you have all sorts of communication parameters, and then you can ask, what is my code doing now? Where is my code? So let's assume your program is running on the server, but it's running like for an hour, and you don't know what it's doing. Then you can ask my contest to open a socket and ask the socket, where is my program now? What is it doing right now? And then you can tell it to do something else maybe. And then, so those are examples of some features that the customers wanted. Another feature that the customer wanted was, for example, not to see a specific bug. Now, my code does not have the concept of a specific bug. So it was difficult. But the use case was the following. Let's assume that in testing I found a bug, but development didn't fix the code yet. So they're going to do it in 2 weeks. And I want to continue to test it, but it crashes on me all the time because of this specific bug. I already know about this bug. I just don't want to see it. So what we did is we had this feature that says you can give it a method name or a class name and say, until you see this class, don't do anything. So basically start testing only once this class is loaded. I didn't say that, but you can, for our program, you can do it at class load, which means that you don't have to instrument in the beginning, or you can instrument the bytecode. In any case, you don't need to compile again.
So for your instrumentations, are you using like a JIT level rewriting?
No. We work on the bytecode. So
When do you modify the bytecode?
So there are 2 options. One of them is we take the bytecode and modify it. This is instrumenting offline. And the other one is at class load. So when you load the class, we instrument it then. The idea of doing it at class, there are trade-offs. So there are scenarios in which you want to do one, and there are scenarios in which you want to do the other. So for example, if you want to instrument the class, if you want to make changes to the way the program behaves, for example, you find out that you don't like something and you want to change it, which I'll show examples, then you want to do it at class load. So this is in the middle of the execution. If you run the test many times, you want to do it in before that because it's more efficient.
So is it an issue for you if you want to modify system classes?
Okay, so system classes, some of them are protected, which means Java checks that you don't change them because otherwise really bad things happen. That's one problem. And the other problem is that when you instrument a class that would call other instrumented classes, you have a problem of recursion. So the first problem I don't know how to solve. If a class is protected, I'm not going to instrument it because it won't let me. The second problem, I mean, for you it might be different, but it's not my classes, so I can't do that. The second problem, I do know how to do, and I check that if I'm seeing recursion happening, I just stop it in the middle. Okay, so let's assume that you have this thing going. Ooh, wrong order of slides. Before I'll get back to the 2 slides. So measuring concurrent coverage. So Contest, one of the features that Contest does is, as I said in the introduction, I was sort of still in charge of coverage in IBM, so every tool that I make has coverage in it. Doesn't have to, but has to. So Contest measure regular coverage. I mean, you can use it to do statement coverage and branch coverage and function coverage. And many people use it for that because it's very convenient. And one of the features that people want me is to have a feature that says don't find bugs. This was actually the feature that people want most out of Contest. And the reason they wanted that is that there are people whose job is to measure coverage. This is what they're told to do. And if they run regression and my finding bugs is on, then the regression crashes. You run the test and some of them get into a deadlock and some of them takes exception. So they can't measure the coverage. Now, you shouldn't measure coverage on a test that fail. But they don't care if tests fail or not. It's not their job. Their job is to measure coverage. So they ask for this feature of says, don't find bugs. But if we leave this point, we get into synchronization coverage. Synchronization coverage is checking that every one of your synchronization statement. So for synchronization statement, it can do 2 things. One is that I was inside and somebody tried to get in and I stopped him. And the other one is that I tried to get in and I was stopped because somebody else was in. So for every synchronization statements, I have two things that I'm trying to do, block and blocked. And if the synchronization statement never did any of them, it never did anything. So I want to check for every synchronization statement. My coverage is I have a single assignment for every synchronization statement which says, did it do anything?
So is it just at least one other thread try to do this, or every other possible?
No, at least one. So unit testing, what do we do with unit testing? So our suggestion for concurrency unit testing is the following. You create tests. You apply our tool to the code or the tools that you have here. And then you run the tests. Now, once you run the tests, if you find a bug, then go fix it. If you find a deadlock, go fix it. So let's assume that now you run the tests that you have, and you didn't find bugs, and you're happy with the results. So the next thing that you do is check if you have good synchronization coverage. If it's sufficient, you're done. So if you have 100% synchronization coverage, every synchronization time you did something, you're done. Your testing is... We have the tools that will tell you for every synchronization if it was covered or not. Which is what I said, if it actually did something. 100%. Every synchronization, at least once, did something. It's not very hard, actually. But in practice, it will be 0 before you start doing something. Now, if your synchronization coverage is not good enough, there could be 3 reasons. So the first one is that your tests are not good enough. So, for example, we once came to IBM in Basingstoke. For those of you who know where Basingstoke is, it's south of London. And we wanted to help them with concurrency bugs. And they said, we don't have a problem. So I said, let's measure synchronization coverage. So we measure and we get 0, which is not a very surprising number. And then we look at the tests. And it turns out that all the tests are single-threaded. So you can't get synchronization bugs. So we explain to them and they say, aha. So we say, okay, let's try. I mean, I can't find any races or deadlocks with single-threaded tests. So we fix it, and they have this, and they run the tests again with multi-threads. And we go to eat lunch, which is a very short affair in England. And we go back, and they tell us, we don't need you anymore. We have enough bugs on our own. Right? So one thing is that your tests are no good. That's one option. So if you need to write new tests and have them run. The second one is that you haven't run them enough times. So it could be that your test can't find a synchronization issue because you have the two threads are executing and they might get to the same place, but they didn't. So you have contests which might try to make it more common, and you run it more times overnight, and hopefully, you'll get better. And if you can get to 100% with both of them, it could be that your design says that there's a synchronization that cannot be executed. So for example, if you have B inside of A, and in every pass B is always inside of A, you cannot get coverage on B. So you have to find out one of the 3 options and do something about them. And once you get to 100%, you're done, as far as unit testing is concerned. And this is not a theoretical issue, and that does not say that there are not bugs left. But the experience is that we have is that while there are bugs left in the code, nobody else will ever find them, which is good enough. Right? I mean, you always know that the code is basically those lines between bugs. So you have bugs there. But if you do that, we didn't find more bugs later.
So in order to get 100%, you have to have a way to reduce the denominator, right? In this case, you have to say it's not going to be the case that for this program, there's going to be some thread waiting on you.
No. To be 100%, all I need is for every, so let's assume for A. To get 100%, I need for every synchronization to at least once the 2 threads try to get into it.
Let's say in this program, there's only 1 thread that uses A. Right? You can never cover that.
Yeah, okay, so I said there's the third issue which would say this is not done. It's like a statement that you cannot get into. And then it's your choice whether you remove it or you say I want it there because of future reasons or whatever.
Do you have some analysis that can tell you that something is not possible?
No, I don't. But what I can tell you is that it's always inside another one. So for example, if B was always inside A, then I will be able to tell you that. But if something is not possible, then I don't know. It's not, yeah. Everything here is dynamic, and I depend on the actual test that happen. So in function and system test, what we tell you to do, this was our original idea, is that you run the tests the way you used to run the test, and hopefully you'll find more bugs. And we ask you to run the test more times. And we also tell you how good the tests are, so if you get synchronization coverage or not. And while you expect to get lower statement coverage in system tests than you would get in unit tests, in synchronization it's not true. You actually expect to get high synchronization coverage. And if you're not doing it, even with contests, with the delays, then you're not testing it well enough. Also, another experience is that you will find the load problems with less threads because they have more connections. We give you aids in debugging and replays that we talked about. Okay, I don't know. So I have two more things that I wanted to show. I'll start with one which I thought was nice. So let's assume that I have the following problem that I want to do. I have a test, I have a program, and I have a test. And what I know about the test is that sometimes it fails and sometimes it doesn't fail. Okay, I have a test that finds a bug. It's a concurrency bug. What I want to show you automatically is the exact line in the code in which the bug is. That's the goal. So I'm not trying to show you an interleaving in which it fails. I want to tell you it's in line 22 of this file. So the question is, how do I go about doing that? And the idea is here, the beginning of the idea, which was not good enough, was that I take the code and I instrument it many times. And every time I do an instrumentation on a subset of the points. So I have 3 points. One I do it on one I do it on those two, and so forth and so on. I run it many times. And sometimes I observe the bug, and sometimes I don't observe the bug. So each point gets a score, which depends on how good it is in finding the bug. So if I instrumented this point 50 times out of the 100 runs, and in those 50 times it found the bug happened half the times, then it will get a score of 0.5. And for this one, it happens a tenth of the time, it will get a score of 0.1. Okay, so I have a correlation here between points and how good they are in helping me find the bugs, if I put a noise in them. And then the first thought was that I would show you those high points, and those will be useful. Okay, so if the bug is very sneaky, like in this program, and I show you those hotspots, which are related to the values, and you look at them, then this is very good in finding the bug. We have a really strange problem, though, that sometimes it's really easy to find the bug. So in testing, if I do noise, it's very easy to find the bug. So I'll give you an example. So let's assume that I have 2 threads. And here it says A equals 4, and here it says A equals 3. And if the order is that this one is first and this one is second, I find the bug. Okay? But actually, usually when I would run it on one machine, this one would be first. So what do I need to do to find this bug? What would happen if I put a sleep statement here? I will find the bug, right? Because then I will come here, go here, and then when I finish here, I will go back to it. If I put a sleep statement here, I will also find the bug. And so forth and so on. So all those points will get high score, which is, it doesn't matter if you put it here or here, all of those points will get high score, which is the same high score. So what's my problem is let's assume that this one got a score of 5, which is high. So I show you this point, and you look at it, and you don't understand what I want, because it's not related to where the bug is. So what I'm going to do, actually, instead, is instead of looking at the score of a point, I'm going to look at the difference between the point and the point after it in the control flow of the program. So all those points will get sort of a 5-ish. But this one will get only 1 because it's not related to the bug. If you put a sleep statement here or not, it doesn't make any difference. So the difference here will be large. And those points with the large difference are the points that I'm going to show to you. So this is an example of that I gave you, how you write the score. Of course, I had to realize that you have to put it on the control flow first. And this is what it looks like in the other program, and it shows some bugs that we didn't see. So actually, I'm running a bit over time. So we do some more experimental things related to healing. And the idea is that we try to make the bug. So our technology in general was in order to make the bug more likely to happen, because this is very useful in testing. But of course, in the field, you don't like that. You'd like to make it less likely to happen. So one of the things that we do is, for example, if you have a deadlock and we find out that you have a deadlock or potential deadlock, we'll hide it. If you have a race, we'll find out. So a race does not mean, so think about it here. This does not have necessarily to be a data race for this problem to occur, because if I had synchronization, I would still have the same problem. So I care about the order in which those things happen, even though there is synchronization. So if I find the orders that I don't like, I will try to make it. I'll try to make them behave only in the order that I like. If I find things that should be atomic and they are not atomic, I'll try to make them behave as if they're atomic in the field. This is only a reasonable idea to do when it makes sense to heal more than to fix. So many times it will be much better if you can actually fix it. But sometimes you don't have access to a program, and you want to make sure that if the program fails, it can sort of fix itself, at least for a while.
So do you expect these user programs should have noise in the production environment?
So they don't, but when they tell me that they're unhappy with what's happening, then I'm going to introduce it and fix it. This is why I said there are scenarios in which you want to introduce noise in the middle. So if as long as the program is running fine, I'm not doing anything. Once it's not running fine, then I will fix it. I will analyze it and fix it and everything.
The kind of the kind of noise that you're introducing is basically time delay.
Yes.
Is there anything else that?
Well, you can use the wait statements, and you can also change values if you want. But changing values is very risky.
Is there any dependency, like a wait will depend on how much sleep is operating some other?
Not currently. So I have quarter of an hour, and I don't want to introduce the next subject because then there will be no time for questions. We have ways which we are talking with Madan here about the deadlocks, which is how we actually find them. And what's special about the way we do it is we collect the information from a number of runs. Usually people did it from a single run because you need to know the object, and the objects are dependent on the execution. When you run it again, it will be a different object, so you don't know how to associate it. But we have a different way to do it. But I think I'll stop here, and I'll be happy to have any questions.
I'm interested in knowing more about what you specifically do to ensure that the bugs don't fail in the field. So is it something that a tool does? Is it something that you do manually?
Okay, so we have a project, a European project. Yeah, it's something that the tool does. Okay. So I'll give a few examples. But first, it's part of a European project called Shadows, which is about healing programs on the run. So let's assume that I found this thing, A and B and A, where it was running. So one thing that I can introduce is I can introduce something called a gate lock. So I found that there is a cycle in its component are A and B, or whatever, A, B, and C. And before you take A and B, I will take a lock called AB. And when you release them, I will release this lock. Okay? So if I do that, I no longer have this deadlocks. However, if I did that, and then I had this situation, which is not a deadlock, after I introduce it, I have a new deadlock. So I have to make sure that once I solve one problem, I didn't cause another. It actually can get complicated. Okay, so this is something that we do for deadlock. For Atomicity, we'll introduce new locks that try to protect specific data structures, so we don't see specific types of races. If there are races, if there are orders which we've seen that with this order it works and with this one it doesn't, we'll try to introduce delays that cause one of them to happen. This is not fixing the bug properly, but it's on the best effort. We do another sort of interesting things for performance, for healing performance problems. So that
This for performance,
This is helpful.
Background.
Yeah, this is help performance. So the following thing is to fix performance problem. So let's assume that you have a client server, and this is request, and this is how many you grant, and this is per time period. So usually the graph would look something like that. In the beginning, the more requests you have, the more you grant, and then you reach the stage in the system where it doesn't handle any more requests nicely. And if the system was not designed well, then something like that will happen. You ask more requests, but you get less of them. You get less granted. So assume that you have a server, and you have clients. And as long as you have less than 10,000 clients, you are fine. But once you have more and they ask for more things, and things get bad. So we have a component that analyzes this picture. And if the picture looks like that, what I want to do is I want it to get it to look like that. And the way I do it is I will slow down the clients. So slowing down is really easy, right? I just instrument them on the fly and I start slowing them down. But the result is that they get the service faster. So I slow them down and the entire system is now running faster because I removed this behavior here. There are also bugs that you can heal this way. So for example, let's assume that there is this buffer, and if you have 300 requests, there's something wrong happening. And we recognize that when the number of outstanding requests is bigger than 300, something nasty will happen. Then we'll not let it get to that number by slowing down the...
So how do you know when to slow down?
Oh, so what I did is somebody else did a performance analysis of the system as it is running, and it got to the fact, and he sees that this picture is happening. This is the picture. Now he tells me, sort of we have healing agent and things. So he tells me slow down. I don't. When I get to here, he tells me slow down. So I slow down a bit. And if he told me slow down too much, then I.
Okay, so you are dynamically measuring the grants requested per second, and then there's feedback.
Right, but it's actually two different components. So usually you have a performance component that will look at what the system is doing in general. And then if the system is behaving this way, then I want to erase this part of the graph. I don't like it. And by slowing down, you make the system run faster, which is maybe counterintuitive.
What do you use for detecting races? Is it the scoring system that you said, or do you use any log set? Or
So for detecting races, we actually use a race detector.
for what? What do you use?
For detecting races, we use our own race detector.
So the tool also reports all these.
If you ask it, usually we don't. So the tool is an open architecture above which you can write anything that you want as a listener. And somebody else wrote the race detector, University in Brno. And we can use that. And putting a lot of noise is sometimes bad, not necessarily from performance, but you find less of the bugs. So think about, you have water falling, right? So the program is like this water falling. And if you introduce delays, lots of delays, then the entire picture would look very similar to what it was to begin with, because you introduce lots of delays. But if you introduce few delays, you stop here and here, then the entire picture will start looking differently and you'll expose more bugs. So it turns out that some of the delays will hide the bugs. Many delays can hide the bugs, and you don't want to have them. So if you can know where to put a few delays, this is good. So one of the things that we do in the beginning, for example, is find out which variables are actually touched by more than one thread, and then we'll put delay maybe only on those. Okay. Yes?
Question about the process. So is it mandatory for, who uses your tool, mostly developers or testers? Is it mandatory to use it?
So it's not mandatory. So as I said, I was talking to Madan. So IBM is a very distributive company. So it's like many different places, and it's not, we can't mandate anything to anybody. The people we work with, so it's been used in both by developers and by. Oh, and I forgot to say one more important thing, which Tom is probably wondering why I didn't say it yet. So we actually teach reviews as well. We teach how to review. This is, yes. And that's one of the major things that we do. But we started it by teaching people how to review for concurrency problems. So the problem is that a regular review will look at a single artifact, and the bug may be due to the fact that you have a number of artifacts. So it's very hard to find concurrent bugs. So when we do a concurrent review, one of the things we teach a role called the devil's advocate. So you walk over the code and there's this guy saying, okay, now we switch. And there are rules as to why you would want to switch now. For example, if you see an if statement and then a synchronization start, yeah, that's a good place to have a thread switch and see if something bad can happen. Okay, so you have this role, and then you don't have to actually, you do it by hand, so you can't go through many interleavings, but usually you find lots of things. So we teach to developers how to do reviews for concurrency, both using the bug patterns and the interleaving review technique, and then how to use the tools. And for system testers, it's fairly easy. It's fairly straightforward.
And for a project who use the tool properly, etc. So what percentage of the concurrency bugs do you catch with the process and the tool?
What I said before, if you do unit testing properly, we haven't seen bugs found later. Concurrency bugs. So this was some of the products that did it, for example, in storage, where you really don't want to see those bugs. But so I'm not saying that they don't exist. They surely exist. But you get it to be clean enough in unit testing that you don't find it later. Okay, so thanks a lot.